The cosmos is a place of breathtaking scale and variety, concealing within its expanse an endless number of stars, each with its own unique and enigmatic nature. Although we identify dozens of new suns every day, circled by equally distinct exoplanets, our search for distant worlds should not cause us to overlook our own solar system, the one location in the universe where conditions have allowed life to arise and thrive. Our solar system is composed of 8 planets, many dozens of moons, and millions of more compact celestial objects, many of which remain poorly understood despite centuries of observation. Today, I invite you to join me on a tour of some of its most compelling destinations. Our expedition will start at the very center of our system, within the blazing interior of its star, the Sun. After navigating past Mercury, which is seared by the star's proximity, we will meet Venus, a world wrapped in dense, layered clouds. From there, we will journey to our homeworld, Earth, and by traveling into the past, we can follow the development of its life, from primitive reptiles to the rise of an even more potent and lethal species, humankind. Our next stop will be the mysterious and barren landscape of Mars, followed by a vast region of cosmic turmoil, where the paths of millions of celestial bodies intersect. After weaving through this maze, we will reach Jupiter and Saturn, along with their intriguing moons. Toward the end of our exploration, we will investigate the shadowed realm of Pluto and its strange moon, Charon. Once we have surveyed their lifeless expanses, our journey will take us even further, past the edge of the solar system itself. We will follow the path of the Voyager spacecraft, which have been tirelessly voyaging toward faraway stars for half a century. On November 21, 2021, the Parker Solar Probe made a historic approach to the Sun, coming within a mere 8.5 million kilometers. This maneuver established it as the very first human-made object to make contact with the solar corona, our star's intensely hot outer atmosphere. But what drove the necessity to venture so near the Sun, surmounting a host of engineering hurdles? What is the Parker probe trying to discover in such scorching closeness to our star? The Sun, first and foremost, is a main-sequence star with an age of approximately 4.6 billion years. It is currently categorized under the spectral class G2V, which defines it as a conventional yellow dwarf. The Sun's surface temperature averages around 5,780 kelvins, or about 5,510 degrees Celsius. Despite this average, its surface exhibits both hotter and cooler areas, and its external corona blazes at temperatures reaching millions of degrees, though it contributes almost nothing to the Sun's visible light. With an average diameter of about 1.4 million kilometers, the Sun is 109 times wider than Earth. Its mass is a staggering 2 × 10⁻³ power kilograms, making it 330,000 times more massive than our world. This accounts for 99.9% of all the mass in the entire solar system. And while you might think of the Sun as a small star, it is in fact larger and more luminous than 80% of all known stars in our galaxy. Hydrogen constitutes 92% of the Sun's volume. As I detailed in a prior episode about stellar evolution, this gas, raised to phenomenal temperatures, is the essential fuel for the thermonuclear processes that power most stars. As hydrogen nuclei merge, they unleash immense energy and are converted into helium, which steadily builds up in the star's core. At present, helium comprises about 7% of the Sun's volume, which corresponds to 25% of its total mass. alongside negligible traces of elements like carbon, oxygen, nitrogen, and iron. The Sun possesses a layered and intricate structure. At its very heart is a tremendous core, which calculations suggest has a diameter equal to 25% of the star's total dimension. The temperature inside the core hovers around 14 million kelvins, and a single cubic meter of its material weighs approximately 150 tons. This is the furnace where thermonuclear fusion takes place, producing the energy that allows our star to shine, converting roughly 4.26 million tons of matter into radiation every second. Encircling this core is the radiative zone, which extends to roughly 70% of the Sun's radius. Matter in this region is so compressed that it cannot mix, which hinders the efficient transfer of heat to the outer layers. Instead, energy is passed along as photons are perpetually absorbed and re-emitted by particles of stellar plasma. According to mathematical simulations, the temperature here drops from 7 million kelvins at its base to 2 million kelvins at its edge, and a single photon from the core can take between 10 and 170,000 years to cross it. Beyond this layer lies the convective zone, the Sun's outermost and comparatively dense shell. In this region, the stellar material has a lower density, allowing massive vortices to form that carry hot plasma upward as cooler material from the exterior sinks down. These convection cells are stable for about 10 to 15 minutes before they dissipate and reform. It is this perpetual churning of matter that generates the magnetic field, extending throughout the inner solar system. The Sun is also surrounded by an atmosphere made of several layers, the lowest of which is the photosphere, the layer that radiates most of the star's visible light, and is what you see when you look at the Sun. The photosphere extends for a thickness of 100 to 400 kilometers, and within this layer, temperatures descend from 6,600 to 4,400 kelvins. Positioned directly above it is the much leaner chromosphere, which is about 2,000 kilometers thick. You can witness this region from Earth during a total solar eclipse, or by using specialized instrumentation. This area is incredibly hot, with temperatures fluctuating between 4,000 and 20,000 kelvins, and its upper boundary is perpetually alive with spicules, vertical streams of hot gas that surge to heights of 5 to 10,000 kilometers. The Sun's most external atmospheric layer is known as the corona, a region defined by massive prominences, flares, and ejections that can expand to sizes of up to 1 million kilometers. The substance that constitutes the corona is exceptionally thin, yet astoundingly hot, with its average temperature hovering around 1 to 2 million kelvins, and sometimes reaching even greater extremes. With every pass, the Parker Solar Probe ventures further into this blazing environment. When we analyze the energy output from the photosphere, it becomes clear that it is inadequate to heat the chromosphere and corona to such severe temperatures, which implies the presence of some not yet understood physical processes that contribute additional heat to the Sun's upper layers. Several scientific theories have been proposed to resolve this temperature paradox. One hypothesis suggests that the chromosphere and corona gain extra energy from the dissipation of waves. An alternative theory centers on the acceleration of charged particles within the star's extraordinarily powerful magnetic field. The Parker Solar Probe was conceived precisely to investigate these questions and explore the strange phenomena observed in the Sun's upper atmosphere. This automated research vehicle is a component of the Parker Solar Probe project from the National Aeronautics and Space Administration, or NASA, which was initiated in 2009. After a lengthy 9-year development period, Parker departed from Earth for good on August 12, 2018, setting its course for the Sun to begin its mission. However, before it could arrive at its final destination, the probe had to execute a series of complex maneuvers. By leveraging the gravitational pull of Venus, Parker incrementally refined its trajectory, moving closer and closer to the fiery sphere at the heart of our solar system. The spacecraft was outfitted with a robust heat shield, and all its instruments were engineered to endure the harshest conditions, while its orbit was designed for brief, intense flybys of the Sun, followed by periods of moving farther away to cool down and transmit its data. The probe's principal objective is to map out the structure and dynamics of the magnetic fields close to the Sun. Parker is also responsible for gauging the flow of energy that pours from the star, capturing samples from the solar wind, and documenting wave phenomena within the solar corona. As a secondary benefit of the mission, remarkable images of Venus and the comet C/2020 F3 have been acquired. To carry out its assignments successfully, the probe is equipped with an extensive array of measurement tools, cameras, detectors for magnetic fields, and sensors for radiation and radio waves. However, a multitude of challenges complicates the execution of the mission. In addition to the critically high temperatures, a relentless stream of ionizing radiation interferes with the functionality of the sensitive measuring equipment. Furthermore, the Sun itself produces intense radio interference, which makes the transmission of the probe's collected data back to Earth a significant hurdle. Nevertheless, Parker presses on with its flight, narrowing its distance to the star on each successive orbit. In late February of 2022, the probe was scheduled to make another journey through the solar corona to collect new information. By 2024, the space between the probe and the Sun's surface is set to diminish to a record-breaking 6.5 million kilometers. According to calculations, the probe's speed at the closest point of its orbit, the perihelion, already hits 163 kilometers per hour second, and will ultimately accelerate to 200 kilometers per second, making it the fastest object humanity has ever launched into space. Unfortunately, the probe's operational lifespan is finite. After making its nearest approach to the Sun, Parker will circle it several more times for about a year. Throughout this period, its velocity will gradually decrease while its instruments are battered by extreme heat and intense radiation. Eventually, the onboard systems will fail, and the probe will begin its final descent into the Sun's fiery depths, where it will be utterly annihilated by the boundless ocean of burning plasma. Before this end comes, however, Parker will have relayed a vast quantity of invaluable data back to Earth, enabling us to advance another step in our exploration of the cosmos, and proving its mission was a success. Although Mercury is situated relatively close to our planet, its exploration has always been plagued by difficulties stemming from its proximity to the Sun. You can only view the planet in the sky when it's near the horizon, either just before sunrise or immediately following sunset. Because of this, ancient astronomers for a long time mistook Mercury for two separate celestial objects, giving them different names. It was only through advancements in observational instruments that scientists were able to start deciphering the enigmas of this unique world. Pulling together the data we have, we can affirm that Mercury is the most diminutive planet in the solar system, even smaller than a few of the larger moons. It has a radius of 2,440 kilometers, which is equivalent to about 38% of Earth's radius. Remarkably, the planet's form is almost a perfect sphere, given that the disparity between its equatorial and polar diameters is no more than 1 kilometer. For a planet of its modest dimensions, Mercury possesses an unexpectedly large mass, weighing in at 3.33 times 10 to the power of 3/23 power kilograms, which is about 5.5% of Earth's total mass. When you compare it to other bodies of similar scale, you'll find it outweighs even the combined masses of Ganymede and Titan, despite both moons being larger in diameter. This surprising density is likely explained by the planet's enormous metallic core, which has a radius of roughly 2,000 kilometers and accounts for about 57% of Mercury's entire volume. Encasing this core is a 100-kilometer mantle of molten silicate rock, topped by a solid crust between 15 and 37 kilometers deep. The planet's surface is heavily pockmarked with craters and displays very few signs of any major geological events. For a long time, the intense glare of the sun made detailed observation from Earth incredibly challenging, and until the latter half of the 20th century, telescopes were our only means of gathering any information about it at all. Our understanding took a monumental leap forward in 1974 with the arrival of the Mariner 10 spacecraft in Mercury's orbit. This pioneering probe successfully photographed 45% of the planet's surface, while also taking crucial measurements of its temperature and magnetic field. Furthermore, Mariner 10's instruments made the landmark discovery of an exceptionally tenuous atmosphere, consisting mainly of helium and trace amounts of other gases. 3 decades later, on August 3, 2004, a successor mission named Messenger began its journey from Earth. After an 11-year voyage, the resilient probe successfully reached its target and, between 2011 and 2015, revolutionized our knowledge by sending back hundreds of thousands of images that mapped nearly all of Mercury. This data provided critical insights into the planet's inner structure, uncovered unique geological formations, and detailed the peculiar way the solar wind interacts with Mercury's magnetosphere. You'll find that Mercury follows a highly eccentric orbit around the Sun, finishing one complete circuit every 88 days. At its closest approach, known as perihelion, the planet gets as near as 0.31 astronomical units to the Sun. At its most distant point, however, that separation grows by 50% to 0.47 astronomical units. What's truly fascinating is Mercury's singular orbital resonance, a characteristic unmatched in our solar system. A single day on the planet lasts for 58.65 Earth days, precisely 2/3 of its year. This unusual timing means that during its closest pass to the Sun, Mercury always presents one of 2 specific hemispheres, creating superheated regions that astronomers refer to as its hot poles. Within one of these hot poles lies the planet's most prominent geological feature, mapped as the Caloris Basin. The name, meaning basin of heat, is incredibly apt, with surface temperatures climbing to a blistering 700 kelvins, or 427 degrees Celsius. This immense impact crater, which spans about 2% of Mercury's surface, is believed to have been formed around 3.9 billion years ago, when an asteroid measuring approximately 100 kilometers across slammed into the planet. The surface of the Caloris Basin is riddled with countless smaller craters, yet its most striking characteristic is a formation of 230 fractures radiating from a central point, each between 1 and 8 kilometers wide. While most of these cracks are under 175 kilometers long, a few reach much further. The origin of this massive fracture system remains a mystery, with current theories suggesting it could be the result of tectonic stress or the gradual cooling of the planet. If you journey north from the fiery Caloris Basin, you'll find a world of profound darkness and cold. Due to Mercury's minimal axial tilt, its polar regions are locked in permanent twilight, with some crater floors never seeing sunlight for millions of years. In the Borealis Planitia near the North Pole, temperatures plunge to just 80 kelvins, where deposits of water ice up to 2 meters thick lie shielded from sublimation by a layer of dust. In stark contrast, nearby sunlit peaks can reach 380 kelvins, or 107 degrees Celsius. And this extreme temperature difference is maintained because the planet's ultra-thin atmosphere is incapable of distributing heat. My tour now takes us further south, to a location on the same latitude as the Caloris Basin, but 3,000 kilometers to its west. Here you can see one of the planet's largest craters, formed about 1 billion years ago, which features a central ring of tall peaks roughly 130 kilometers across. The rocks inside this ring have a distinct reddish color, hinting at ancient lava flows from one of Mercury's final volcanic episodes. This crater is also home to the planet's lowest point, plunging 5,380 meters below the average surface level, and is surrounded by expanses of dark, smooth plains. As we journey further south, you'll see an immense serrated cliff named Enterprise Rupes, which extends for 820 kilometers toward the northeast. This feature, which can tower several thousand meters high, is the largest of many similar scarps found across Mercury. Geologists believe these distinctive formations arose as the planet cooled, causing its lithosphere to shrink and buckle into enormous ridges. You'll notice that almost half of Enterprise Rupes lies inside Rembrandt, Mercury's most massive crater, measuring 1,600 kilometers across. Within this expansive basin, you can find a variety of smaller geological structures, including minor mountain ranges between 1 and 10 kilometers wide that run for up to 180 kilometers. The crater floor itself is crisscrossed by a network of deep fractures, forming an intricate web-like design. By examining the surface of Rembrandt crater, we hope to gain deeper insights into Mercury's internal composition and the dynamic processes happening deep inside. For all the attention from astronomers and our technological progress, Mercury continues to be a largely enigmatic and underexplored world. But its mysteries won't remain hidden for much longer, as the Bepi-Colombo research probe, a collaborative effort between the European Space Agency and Japan, is currently closing in on the planet. The probe's onboard instruments are designed to collect information about the makeup of Mercury's surface and atmosphere, analyze its magnetosphere and interaction with the solar wind, and give us a more precise understanding of its topography. Bepi-Colombo has already completed flybys of Mercury, but it must execute several more intricate maneuvers to reduce its speed and achieve a stable orbit. Projections indicate this will happen by 2025, at which point its mission of gathering and sending back data will commence. Now let's turn to Venus, the second planet from the Sun, which orbits at a distance of 0.72 astronomical units, and completes its year in about 225 Earth days. Approximately every 584 days, Venus makes its closest approach to our world, narrowing the gap to about 0.25 astronomical units. What's fascinating is that during these encounters, Venus consistently presents the same face to Earth, though we still don't know if this is a result of Earth's tidal pull or just a remarkable coincidence. When you look at its physical traits, Venus shares many similarities with our own planet. Its average radius is 6,052 kilometers, which is 95% of Earth's, and its mass is 4.87 times 10 to the 24th power kilograms, or 82% of Earth's mass. The planet rotates on its axis very slowly, taking around 243 Earth days to complete one turn, with its rotational axis tilted by only 3 degrees from the ecliptic plane. For a very long time, Venus hid its true character from scientists beneath a thick atmosphere and an impenetrable layer of clouds. This shroud of mystery gave rise to some of the most imaginative theories and speculations you can imagine. Some people proposed that a highly developed civilization existed under the planet's opaque covering, while others envisioned a world populated by strange and exotic creatures. Of course, until we could see beneath the clouds, these concepts could be nothing more than conjecture. A major breakthrough in our understanding came with the advent of space probes and radar technology. We discovered that radio waves of specific frequencies could penetrate the planet's gaseous shell and bounce back from the solid rock below. Using this principle, the Pioneer Venus 1 spacecraft created the very first maps of the Venusian surface back in 1978. While these initial maps were later enhanced by other automated probes, their precision was limited to about 1 to 2 kilometers, meaning they could only reveal the most prominent geological formations. To get a clearer picture, a specialized mission called the Magellan Research Probe, equipped with a powerful radar system, was dispatched to the planet. From 1990 to 1994, Magellan mapped 95% of the surface of Venus and sent the images back to Earth, achieving a resolution of around 120 meters. To this day, the information gathered by Magellan remains our most comprehensive and precise data on the planet's topography. Before we explore the surface of Venus in more detail, it's important for you to understand its internal composition. The most widely accepted theory suggests that Venus possesses a metallic core at its center, which makes up about 25% of its total mass. Since observations confirm that Venus has no magnetic field of its own, we believe its core is probably solid. And this core is enveloped by a molten silicate mantle that extends for roughly 3,000 kilometers. Above the mantle lies a solid crust with an average thickness of about 16 kilometers. Because of the extreme temperatures and the highly viscous nature of the rock, the lithosphere of Venus doesn't break into tectonic plates, which greatly limits its geological activity. You'll also notice a relative scarcity of large impact craters on its surface. Instead, massive plains of solidified basaltic lava cover huge areas of the planet. Some of the formations we've found on Venus are entirely unique and have not been observed on any other world in our solar system. These include features called tesserae, which are extensively fractured regions of terrain that look like tiled floors. You can also find other distinct structures known as arachnoids and coronae. These are circular or oval formations that can be hundreds of kilometers wide. While they may look like impact craters, they were actually formed by tectonic activity, not by collisions with objects from space. If you were to look at processed photos of Venus, you'd still struggle to make out any specific surface features without a trained eye. To get a clearer picture, we'll turn to a topographic map that uses distinct colors to show different elevations. Your attention is immediately drawn to Aphrodite Terra, the most expansive elevated area, which serves as one of the planet's quasi-continents. This colossal landmass, defined by its highly intricate mountain ranges, extends along the equator for up to 18,000 kilometers in length and 5,000 kilometers in width, with a total area comparable to the continent of Asia. Exploring Aphrodite Terra reveals 3 main sections. In the eastern portion of this continent, you'll find Mayat Mons, the tallest volcano on Venus. It rises about 5 kilometers from its base to its peak, with its total elevation above the planet's mean surface level ranging from 8.3 to 8.8 kilometers. Although Mayat Mons is currently dormant, geological evidence points to a fairly recent eruption, supported by the presence of distinct solidified lava flows and a complete lack of impact craters on its flanks. Moving to the western section of Aphrodite Terra, you encounter Ovda Regio, a fascinating area for studying tectonic activity. The mountain chains here run in multiple directions, which suggests that the crust is being subjected to several different deforming pressures at the same time. Furthermore, scientists have identified deep cracks showing evidence of lava extrusion, representing some of the most peculiar volcanic structures found anywhere on Venus. Journeying to the continent's far western boundary brings you to the targeted landing zones for 4 probes from the Venera program, 2 of which were lost in the dense atmosphere before ever touching down. These sites are all located within the southern reaches of an immense basin called Lavinia Planitia, a lowland that extends for a great distance along the periphery of Aphrodite Terra. Despite being named a plain, this area's topography is actually a complicated tapestry of different geological structures. The prevailing theory is that over hundreds of millions of years, tectonic pressures sculpted the crust into a series of ridges and folds. At the same time, lava erupted from fissures, spreading out and hardening to create smooth basaltic flats that filled in the lower elevations, resulting in a landscape with both level stretches and prominent highlands. Another area of great interest is Beta Regio. This huge territory shows up as a very bright feature in radar imagery, which is why it was among the initial surface formations on Venus to be named. Beta Regio is a raised, roughly circular landmass spanning about 2,500 kilometers in diameter. It was in the eastern section of this region that the Venera 9 and Venera 10 probes successfully touched down in 1975, transmitting the very first images from the planet's surface. In addition to taking pictures, these landers also recorded atmospheric data and examined the composition of the soil, discovering it was comparable to basalt found on Earth. This information has led to the hypothesis that Beta Regio is the most massive volcanic complex on Venus, positioning it as the prime candidate for locating currently active volcanoes. Our tour now takes us northward to Ishtar Terra, the second largest of Venus's continental landmasses. This region extends for about 8,000 kilometers from west to east and 2,500 kilometers from north to south. Its total surface area measures approximately 8.5 million square kilometers, which makes Ishtar Terra just a bit larger than the continent of Australia. At the heart of Ishtar Terra, you find the Maxwell Montes, the most elevated mountain range on the entire planet. These peaks soar 11 kilometers above the average surface level and stand a full 7 kilometers higher than the adjacent terrain. The central, highest part of the range forms a relatively level plateau, measuring about 400 by 200 kilometers, where the variations in height are no more than 1.5 kilometers. Remarkably, Maxwell Montes is the chilliest location on Venus, where temperatures dip to a mere 380 degrees Celsius, and the atmosphere is about half as thick as at sea level. Even so, this air is still 44 times denser than the atmosphere on Earth. The region also stands out for its brightness in radar scans, indicating that the mountain peaks and slopes are probably coated in a material like pyrite or hematite that is highly reflective to radio waves. As you consider the surface of Venus, it's natural to ask yourself if these incredible and enigmatic locations will forever remain beyond human reach. Does a possibility exist that we might one day make our presence known on the face of this world? A planet so near to us, and yet so fiercely unwelcoming. The reality is that Venus has an atmospheric pressure roughly 93 times greater than Earth's, while the average surface temperature is a staggering 737 kelvins, which is 464 degrees Celsius. The environment is so utterly severe that even robotic probes engineered specifically for Venusian exploration can function for only an hour or so before they fail. You might find the concept of colonizing other worlds to be the stuff of science fiction. Yet, if you look at Venus, you'll find layers in its atmosphere where the conditions, both temperature and pressure, are surprisingly similar to those on Earth. In fact, proposals from as early as the 20th century suggested we could build floating habitable bases there, suspended on specialized aerostats within the planet's gaseous shell. While the actual viability of these ambitious projects is still debated, one thing is certain: Venus holds its secrets close, waiting for future explorers to one day uncover them. Now, I want you to picture Earth's biosphere about 252 million years in the past, when it faced a cataclysm of unimaginable scale. In what was a mere blink of an eye in geological time, life was nearly extinguished, with the planet losing 96% of its marine species, 70% of its land vertebrates, and an estimated 83% of all insects. Even now, the precise reasons for this mass extinction remain one of science's greatest mysteries. But despite this horrific event, life itself was not eradicated from our world. Instead, this tragedy cleared the stage for a completely new age, paving the way for the emergence of history's most celebrated ancient behemoths, the dinosaurs. This event, which we call the Great Permian Extinction, serves as the critical turning point that initiated the Mesozoic Era. This entirely new chapter in Earth's geological saga began 252 million years ago and spanned for 186 million years. During this vast stretch of time, our planet was undergoing dynamic transformations, slowly shaping into the world you know today. The most significant geological event was the breakup of the supercontinent Pangaea, which first split into the two massive land masses of Laurasia and Gondwana before fragmenting further into our familiar continents. The creation of these numerous isolated lands, divided by seas, fostered the growth of unique ecosystems and drove the evolution of new adaptations. The climate of the Mesozoic was, on the whole, the warmest period in the entire history of complex life, and for its duration, you wouldn't have found any permanent ice, even at the poles. The Mesozoic Era itself is separated into three distinct periods, the first of which is known as the Triassic. This initial stage commenced around 252 million years ago and continued for approximately 51 million years. Throughout this time, deep subterranean forces had only just begun the process of tearing Pangaea apart, so the supercontinent remained largely whole. It was also during the Triassic that the Ural Mountains, one of the planet's most ancient mountain ranges, finished their formation, standing at that point as a young and towering range. The climate of this period was predominantly hot and arid, which resulted in the expansion of vast deserts and the shrinking of inland seas and lakes. For a large portion of the Triassic, the oxygen in the atmosphere was quite low, hovering between 10 to 15%. However, around 215 million years ago, this level experienced a dramatic surge. While we don't know the exact cause, scientists speculate this oxygen spike could be linked to the evolution and proliferation of specific types of aquatic or terrestrial plants. At the time, the vast majority of the planet's plant life was composed of ancient seed ferns, but they were steadily being replaced by more evolutionarily advanced groups. You would have seen the rise of cycads, ginkgo trees, and early conifers, many of which have relatives that still survive in the modern era, though their diversity has greatly diminished. In the oceans, marine life was forging its own evolutionary path after the devastation of the Permian extinction. The seas were gradually being repopulated by creatures like turtles and bony fish, while the role of top predator was claimed by the first members of the ichthyosaur order. Later on, the ichthyosaurs would become reptiles, perfectly adapted to an aquatic existence. But during the Triassic, these animals were still quite primitive. A prime example for you is Spondylus, which thrived from 240 to 210 million years ago. This massive marine reptile could grow to between 6 and 10 meters long and sustained itself mainly on fish. It had a long, slender body, with a flexible tail that made up about half its length, and a large head with a tapered snout full of small, sharp teeth. The limbs of Spondylus had evolved into flipper-like appendages, though it probably used them just for steering and stability in the water. Its skeletal structure indicates that it swam by moving its entire body in an undulating motion, suggesting it was a rather clumsy creature. On land, the most defining fauna of the era were the archosaurs, which were the ancient ancestors of not only dinosaurs, but also crocodile-like reptiles and birds. By the middle of the Triassic, these ancient archosaurs had diversified significantly, but a long and fierce battle for survival still lay ahead of them. It wasn't until the end of the Triassic that the dinosaurs began to truly establish their dominance across Earth's biosphere. Their ascent coincided with a sharp increase in their size, which occurred around the same time as the surge in atmospheric oxygen. Today, the image of these fearsome lizards is ingrained in our collective consciousness, thanks to countless films and books. Yet, their immense fame often casts a shadow over other fascinating and equally important animals from that time. For instance, consider the small creature Alligophus, which lived during the late Triassic period, roughly 200 million years ago. This tiny, nimble animal was a type of cynodont, an ancient group of creatures that differed from true mammals in only a few minor details. Alligophus possessed a slender, agile body, about 50 centimeters in length, was covered in fur, and had an appearance very similar to a weasel. It was a warm-blooded herbivore that was remarkably widespread, inhabiting areas that now make up North America, Europe, and China. While we can't be certain if Alligophus had a pouch, the dimensions of its pelvic bones strongly suggest that its young were born extremely small, a feature you see in modern marsupials. Moreover, there's a very high likelihood that these animals were capable of nourishing their babies with milk, another key trait that brings them incredibly close to the mammals we know today. It is theorized that Alligophus constructed burrows and nurtured its young, implying a fairly advanced level of intelligence for its time. These creatures tragically vanished at the dawn of the Jurassic period, likely because their primary food sources dwindled, but they are still regarded as the most ancient animals with a strong resemblance to modern mammals. The Triassic period concluded with a catastrophic mass extinction event. A vast number of species, including many amphibians, certain archosaurs, other reptiles, and numerous types of plants, were wiped from the planet. Among the suspected triggers for this disaster are widespread volcanic eruptions, significant changes in sea level, and severe, sudden shifts in the global climate. In the aftermath, this extinction opened up a multitude of ecological niches, which created the perfect opportunity for dinosaurs to solidify their dominance in Earth's evolutionary theater. The historical period that followed in the Mesozoic Era is known as the Jurassic. It commenced roughly 201 million years ago and concluded around 145 million years ago, spanning a total of about 56 million years. This era was characterized by enormous tectonic shifts and planetary transformations. It was during the Jurassic that the supercontinent of Pangaea completed its fragmentation, breaking into several large land masses divided by shallow oceans. This process of continental isolation resulted in the development of separate and distinct biosystems, meaning that the animals and plants evolving on one continent might be entirely different from those on another. If you were to view a map of Earth from that time, you could already make out the nascent shapes of some modern continents by the period's end, though they would be situated in locations that would seem completely alien to us. The Jurassic climate was generally warm and humid, but it experienced a comparatively short cooling phase as the period drew to a close. Immense stretches of land were blanketed in tropical forests, dominated by cycad trees that looked similar to today's cypresses and pines. On the terrestrial stage, the age of dinosaurs truly began to flourish. Their astonishing diversity permitted them to occupy the majority of ecological niches, establishing their reign in nearly every environment. These creatures ranged in size from small lizards no bigger than a house cat to some of the most colossal giants ever to walk the Earth. The Jurassic saw the widespread proliferation of herbivorous dinosaurs with similar body plans known as sauropods, which included familiar names like Brachiosaurus, Brontosaurus, and Diplodocus. The largest of these, the titanosaurs, could achieve lengths of 25 to 30 meters, and their body mass might have surpassed an incredible 75 tons. A truly fascinating characteristic of the sauropods was the feature known as the sacral brain. This was an enlargement in the posterior part of the spinal cord that was once thought to contain 20 times more nervous tissue than the brain itself. The current scientific consensus, however, is that this sacral cavity was more likely filled with a gliogenic body, which served as an energy reserve for the gigantic lizard's nervous system. While dinosaurs reigned supreme, other animal groups continued their evolutionary journeys in their shadow, including early mammals, various reptiles, and arthropods. In the oceans of the Jurassic, bivalve mollusks very similar to modern species became common, while the apex predators were an assortment of aquatic reptiles, most notably the ichthyosaurs and plesiosaurs. To give you a sense of their evolution, if we compare the Jurassic Ophthalmosaurus to the more ancient Symbospondylus from 180 million years ago, we see a creature that grew up to 6 meters long, with a highly streamlined body and a vertical tail finely tuned for aquatic propulsion. This marine reptile possessed a dolphin-like physique, complemented by a graceful yet powerful crescent-shaped vertical tail. It is believed that Ophthalmosaurus breathed air at the surface, but had the capacity to stay submerged for as long as 20 minutes. It could reach speeds exceeding 7 kilometers per hour and was capable of diving to depths of approximately 600 meters in search of prey. The structure of its teeth suggests that its diet was composed mainly of mollusks, including various types of squid. Another remarkable attribute of this animal was its eyes, which measured about 10 centimeters in diameter and were reinforced by a protective ring of bony plates. This feature leads scientists to believe that Ophthalmosaurus had exceptional vision in low-light conditions, an adaptation that would have allowed it to hunt effectively in the deep, dark waters inhabited by other large predatory reptiles. The final chapter of the Mesozoic Era is the Cretaceous period. It started 145 million years ago and continued for about 79 million years, which makes it the longest single stage of the Mesozoic. Throughout this entire period, the continents persisted in their slow drift apart from one another. India broke away from Africa and embarked on its long, slow journey toward Asia, a process that formed the Indian Ocean. South America also detached itself and began to shift westward. By the conclusion of the Cretaceous, the geographical outlines of Africa, Australia, Greenland, and both North and South America had started to look much like their present-day forms, while Europe and Asia were just beginning to coalesce. The climate during the Cretaceous was comparatively cool. Between 185 million years ago, the average global temperature rose for a time before it began to cool down again, a trend that lasted until the end of the era. This was the time when Tyrannosaurus and Triceratops roamed the Earth, two of the most famous dinosaurs and enduring symbols of the entire Mesozoic. A far more consequential development during the Cretaceous, however, was the widespread appearance and diversification of angiosperms, which are flowering plants. First came trees, and later grasses, which together formed extensive new types of forests. These plants anchored the soil layer, enhancing its fertility, and created a vital food source for a multitude of emerging species. This botanical revolution acted as a powerful evolutionary catalyst, driving a significant increase in the diversity of mammals and, to a lesser extent, birds to degree, certain herbivorous dinosaurs. Despite the absolute rule of reptiles across every ecological niche, mammalian evolution continued unabated throughout the Cretaceous period. The variety of mammal species gradually expanded, and by the close of the era, we can clearly identify distinct evolutionary groups taking shape, such as early ungulates, insectivores, predators, and even primates. As an example of this growth, one of the largest mammals of the Cretaceous period was Repenomamus, a creature that lived approximately 125 million years ago. This creature grew to a length of 1 meter and weighed between 12 and 14 kilograms, with an external appearance thought to be similar to the modern Tasmanian devil. The structure of its teeth identifies Repenomamus as a predator, though its short, awkward limbs imply it likely scavenged as well. A fascinating fossil discovery supports its hunting capabilities. A skeleton was found containing the remains of a small dinosaur, Psittacosaurus, in its stomach, which suggests that some mammals of the era actively preyed on smaller dinosaur species. For an extended period, the oceans were the domain of enormous swimming reptiles like ichthyosaurs, plesiosaurs, and mosasaurs. Their reign came to an end roughly 90 to 95 million years ago, when their populations plummeted during the Cenomanian-Turonian extinction event. This massive die-off is tied to a dramatic drop in the ocean's oxygen levels, potentially triggered by a surge in underwater volcanic activity. The final stage of the Cretaceous marked the coldest phase of the entire Mesozoic era, forcing all life, including dinosaurs, to adjust to the falling temperatures. It was in this environment, about 70 million years ago, that an incredible dinosaur named Nanoxaurus thrived north of the Arctic Circle in what we now call Alaska. Although it was a close relative of the colossal Tyrannosaurus rex and shared a similar appearance, it was significantly smaller, measuring about 6 meters long and weighing only 500 kilograms, a mass 8 to 9 times less than its gigantic cousin. Scientists believe its diminished size was an adaptation to the limited food available in the severe climate of the far north. To survive among the snow-covered landscapes and during the polar night, Nanooksaurus developed several key traits. It was likely warm-blooded, possessing a metabolic rate similar to modern mammals, and was insulated by a thick downy coat to conserve heat against the bitter cold. These features point to an agile and energetic predator, but the darkness of the polar night made traditional hunting difficult, suggesting it evolved a keen sense of smell and acute night vision to locate prey. The short and cool summers in these high latitudes meant that extra warmth was essential for the successful development of its young. Consequently, it is believed that Nanooksaurus, along with other northern dinosaurs, would have incubated its eggs and actively nurtured its offspring. Furthermore, analysis of its fossilized remains indicates an intelligence level on par with that of many contemporary bird species. Despite these remarkable adaptations, Nanooksaurus could not escape the cataclysm that ended its time on Earth. Approximately 66 million years ago, the Cretaceous-Paleogene extinction event annihilated all non-avian dinosaurs, marine reptiles, pterosaurs, and countless other species. Yet, these magnificent creatures left an indelible legacy, as the ecological voids they left behind were rapidly filled by birds and mammals. This transition ushered in the Cenozoic Era, which eventually produced a unique species, Homo sapiens, a being that has proclaimed itself ruler of the natural world, with a future that remains unwritten. The cataclysm that ended the age of dinosaurs initiated a new geological chapter, the Cenozoic Era, which started 66 million years ago and extends to the present day. This new era's first period, the Paleogene, spanned 43 million years and saw dramatic changes to the planet's face as India drifted across the ocean to collide with Asia, thrusting the Himalayas skyward, while Antarctica became encased in kilometers of ice. Over the first 10 million years, the biosphere slowly healed, allowing resilient and adaptable mammals to claim the roles once held by dinosaurs, giving rise to creatures like the fearsome Andrewsarchus, the massive Indricotherium, and the aquatic Archaeoceti, which were the early relatives of modern whales. As life continued to adapt, the Paleogene gave way to the Neogene period around 23 million years ago, a stretch of time lasting for about 20 million years. Its first and longer epoch, the Miocene, was characterized by a slow, progressive cooling of the planet. During this time, polar ice sheets expanded, sea levels fell, and great mountain chains like the Alps and the Andes were formed. A direct result of these tectonic shifts was the isolation of the Mediterranean Sea from the global ocean, causing it to almost completely evaporate. What remained was an immense, salt-encrusted basin, where the air pressure on the floor was 1.5 times normal, a desolate landscape, dotted only by a few hypersaline lakes. The Miocene world was populated by a host of extraordinary creatures. In the thick jungles of Asia, you would find Gigantopithecus, colossal relatives of orangutans that stood over 3 meters tall and weighed as much as half a ton. The steppes were terrorized by entelodonts, bull-sized, hooved beasts that were both predators and scavengers. Meanwhile, the ocean's depths were ruled by the megalodon, the most massive carnivorous shark ever to have existed on Earth. Then, just over 5 million years ago, a tremendous earthquake rocked the region we know as Gibraltar. This cataclysm shattered the rock barrier that had held back the Atlantic Ocean for hundreds of thousands of years. In an event of unimaginable scale, Millions of tons of seawater cascaded into the vast, desiccated basin, refilling the Mediterranean Sea. Calculations indicate the force of this deluge was roughly 40,000 times greater than Niagara Falls, and it required a mere 2 years to refill the entire sea. In the process, massive salt deposits were sealed away forever beneath kilometers of water. This monumental occurrence, named the Zanclean Flood, marks the start of the Pliocene epoch, a period that spanned 2.745 million years. During this era, the continents had largely shifted into the positions you would recognize today, though certain topographical features were only just beginning to take shape. For instance, early in the Pliocene, a broad strait still divided North and South America, and the Rocky Mountains were just starting their ascent. In the first half of the epoch, the Earth's climate was considerably warmer, with the planet's average temperature hovering 2 to 3 degrees Celsius higher than our current baseline. This extra warmth was not spread evenly across the globe. While the climate in tropical latitudes was similar to what it is now, the northern regions experienced much milder conditions. An Arctic ice cap would form only intermittently, allowing dense coniferous forests to flourish deep into the north of Eurasia. It is important to note, however, that the continent's edge was situated slightly south of its present-day location, because the heightened temperatures kept the average sea level about 25 meters higher than it is today. Meanwhile, the African continent was home to the most ancient ancestors of humanity that we know of, Sahelanthropus and Orrorin. The fossilized remains of these primates have been dated to between 4 and 6 million years ago. Their physical structure was still a long way from being human, and you would certainly classify these creatures as advanced apes. Yet, they had already taken the first crucial step onto a new evolutionary path. Anatomical details in the discovered skeletons point toward an emerging tendency for walking on 2 legs, even though characteristics of a tree-dwelling lifestyle remained very prominent. Furthermore, the cranial volume of these beings exceeded that of chimpanzees, and their tooth structure was closer to that of later species. So what could have compelled these ancient primates to undergo such a radical transformation? The likely answer can be found in a major geological event that occurred around 3 million years ago. The continental plates of North and South America collided, triggering a rapid uplift of mountain ranges. This collision blocked the strait between the continents with the Isthmus of Panama, which in turn stopped the free circulation of warm ocean currents. At roughly the same time, the Rocky Mountains grew significantly in height, creating a massive barrier that disrupted air currents between the Atlantic and Pacific. The combined effect of all these factors eventually set in motion a gradual cooling and partial glaciation of the planet. An immense ice shield encased the North Pole, a glacier tons in weight covered Greenland, and the expanse of Africa's forests shrank considerably, replaced by steppes and savannas. For ancient primates perfectly adapted to life in the trees, the canopy was an ideal home. It was safe, comfortable, and provided abundant food. However, the global climate shift drove many species to extinction by destroying their natural habitats, causing them to vanish from the Earth. The survivors were those who were compelled to change in order to endure the new conditions. Currently, the most developed and well-supported theory of human origins is known as the savanna concept. It proposes that the scarcity of familiar food and vegetation forced our ancestors to brave the savanna, an environment filled with unknown perils. These early ancestors already possessed some ability to move on 2 legs and use primitive tools, skills common to all primates that proved decisive for surviving in this new world. The savanna lacked the easily digestible fruits and berries they were used to, and they couldn't consume tough grasses and leaves. For them, the key to survival became the consumption of animal protein, which fundamentally altered their way of life. Our ancestors weren't powerful enough to hunt large animals on their own, but the evolution of bipedalism shifted the odds in their favor. Walking upright not only increased their movement speed several times over, but also gave them a higher vantage point to spot both prey and predators from a distance. This vertical posture also freed up their strong hands and dexterous fingers, making it far easier to wield a stick or a sharpened stone as a tool or weapon. By banding together in small tribes, the new savanna dwellers could successfully hunt, or, at the very least, chase other predators away from their kills. It is theorized that the necessity for coordinated action during these activities ultimately spurred the development of the brain and the emergence of primitive speech. This slow development, unfolding over several million years, transformed ape-like creatures like Ardipithecus and Sahelanthropus into beings with distinctly human characteristics. This evolutionary path led to the appearance of the Australopithecines, intelligent but small creatures who inhabited Africa between 4.2 and 1.8 million years ago. Analysis of their discovered remains indicates their height was between 120 and 140 centimeters, with a weight of around 40 kilograms. Unlike other primates, Australopithecines primarily moved on two legs, though their posture was still somewhat stooped, and their brain, while larger than an ape's, was not significantly different in its internal structure. We know that Australopithecines lived in groups and were capable of cooperating for hunting and defense. Research indicates that the earlier species used only found objects as tools, but later generations learned to craft the most basic instruments for labor and self-protection. In spite of these adaptations, most individuals did not live past 20 years, succumbing to diseases, injuries, and attacks from wild animals. The predators of that time apparently considered Australopithecines to be just another source of food. For example, the Dinophilis, a species of cat that was a distant relative of the later Smilodon, lived during this period. Excavations suggest they often established their territories near Australopithecine encampments, clearly targeting them as prey. While only slightly larger than a modern leopard, Dinophilis was built much stockier and was considerably more powerful. Imagine facing predators weighing up to 120 kilograms and standing about 70 centimeters tall at the shoulder. Defending yourself alone against such a creature would have been nearly impossible, suggesting that our ancestors' survival likely depended on their ability to work together. While most animals from that era resembled those we know today, some were true monsters, like the various species of flightless predatory birds from the Phorusrhacidae family that roamed North and South America. The largest of these Phorusrhacidae could grow to a height of 3 meters, possessing enormous skulls dominated by a formidable beak. Their long, powerful legs enabled them to achieve astonishing speeds. Fortunately for our ancestors, they never had to confront these terrifying birds, as the Phorusrhacidae went completely extinct around 100,000 years ago, long before ancient peoples settled the Americas. Meanwhile, the jungles of Asia were home to the Dinotherium, a colossal creature standing between 3 and 4 meters tall. Among all land mammals that have ever existed on our planet, only the Indracotherium and mammoths surpassed it in size. It's believed these distant relatives of elephants dwelled in the forests of Asia and Africa, primarily feeding on the leaves of trees. Their trunks were likely shorter and more robust than those of modern elephants, and their lower jaws were distinguished by a pair of massive, downward-curving tusks. A momentous event, known as the Brunhes-Matuyama magnetic inversion, took place 258,800 years ago. During this phenomenon, the Earth's magnetic poles switched places, causing the lines of the magnetic field to reverse their direction. This transition was marked by a severe weakening of the planet's protective shield, which allowed harmful cosmic rays to penetrate to the surface and impact all living organisms. Although this inversion lasted for only about 15,000 years, a mere blink in geological time, it triggered the mass extinction of several species and is now regarded as a key marker for the start of a new geological period. The Anthropocene period is split into two distinct epochs. The first of these, the Pleistocene, commenced 288,000 years ago and concluded just 12,000 years ago. The climate during this epoch was defined by cyclical cooling phases that led to the expansion of glaciers. It was during the warmer interglacial periods that the evolutionary process began to shift, leading the Australopithecines to diverge into two main primate branches, the Paranthropus, all of which are now extinct, and the genus Homo, which includes modern humans. For a considerable stretch of time, however, all three of these hominid branches coexisted, locked in a state of competition and a constant struggle for survival. You should understand that human evolution was not a straight, linear path. It was a complex process with numerous dead ends and offshoots. At various points in history, our planet has been inhabited by at least 24 different species that could, in some capacity, be considered human. I must emphasize that the evolution of our species and its ancestors is a topic of intense interest, with details being continuously revised. Remember that evolution operates on an extremely slow timescale. For two species to fully diverge, a period of at least 2 to 3 million years is typically needed, during which they can still interbreed and produce viable offspring. The entire history of our own genus, Homo, spans only about 2.5 million years, a time frame that roughly doubles if we include our most ancient ancestors. Many of these early human populations occupied neighboring territories, which means that a wide variety of hybrids undoubtedly emerged in nature. Furthermore, the intraspecific variability among humans is quite substantial. Men and women display noticeable physical differences, and individuals from different racial backgrounds exhibit a remarkable degree of diversity. Despite their advanced traits, Australopithecines were still fundamentally more ape-like than human. The first creature widely accepted as a member of the human genus was Homo habilis, also known as the handyman. Archaeological evidence indicates that Homo habilis inhabited Africa between 2 million and 1.5 million years ago. This species possessed a more developed brain than the Australopithecines and had the capacity to create primitive tools. Individuals of this species stood around 1.2 meters tall and seldom weighed more than 50 kilograms. A crucial evolutionary development was the structure of their foot, where the big toe was aligned with the others, just like in modern humans, suggesting a full adaptation to walking upright on two legs. The anatomy of their jaw also points to a slowly emerging capacity for articulate speech. As evolution continued, Homo ergaster, or working man, and Homo erectus, the upright man, emerged approximately 2 million years ago. Some researchers view them as closely related but separate branches of evolution, while others consider them subspecies of the same species. Through extensive migration, these early humans spread from Africa into Asia and Europe, sparking numerous new evolutionary pathways, one of which ultimately gave rise to Homo sapiens. Ancient humans, Whether they were Neanderthals or Homo sapiens, lived in tribal groups and maintained a nomadic existence based on hunting and gathering. This lifestyle compelled them to migrate constantly, leading them to settle in new and uncharted territories. Over time, these primitive tribes gradually populated every continent on Earth with the exception of Antarctica. The colonization of Australia began around 50,000 years ago, and about 24,000 years ago, humans first ventured across the Bering Land Bridge into North America. The migration of these ancient tribes coincided with a period of mass extinction among the Pleistocene fauna. In the span between 50,000 and 10,000 years ago, the world saw the last of the saber-toothed cats, the woolly mammoths, and the giant ground sloths known as Megatherium. This wave of disappearances forever altered the planet's ecosystem, marking the end of an era for many of the great beasts that once roamed the Earth. In their wake, other predators that could not endure the fierce competition for sustenance also vanished. Humanity might have met a similar end, but the last ice age concluded approximately 12,000 years ago. Our planet's climate grew warmer and more humid, which ultimately set the stage for the emergence of comprehensive agriculture. This pivotal moment, known as the Neolithic Revolution, signaled the close of the Pleistocene and the dawn of a new era for Earth, the Holocene, a period defined by the swift ascent of human civilization through technological and societal advancement. Now, having ventured into the unexplored territory beyond our world, it is uncertain where this journey will ultimately take us. Mars orbits the Sun at a distance roughly 1.5 times greater than that of Earth. Its radius is nearly half the size of our own planet's, while its mass constitutes only about 10.7% of Earth's. Consequently, the gravitational pull on the Martian surface is almost 3 times weaker than what you experience here, and its temperatures fluctuate dramatically, from a frigid minus 153 degrees Celsius at the poles to a comparatively balmy plus 35 degrees Celsius along the equator. The total surface area of Mars is comparable to the land mass of all of Earth's continents combined, showcasing an incredible variety of landforms. While some of these features are reminiscent of terrestrial landscapes, others represent geological formations that are entirely unique and awe-inspiring. At present, 8 automated research stations orbit the planet, meticulously observing its surface. Analyzing the data they've gathered allows you to easily spot an enormous, bright feature situated in the planet's western hemisphere. This prominent region is home to the largest volcano in our solar system, a colossal mountain named Olympus Mons, and it is here that our expedition across the Red Planet commences. Olympus Mons towers 26 kilometers above the adjacent plains, making it about 2.5 times taller than Mount Everest. It is thought to be a shield volcano, constructed from countless layers of hardened lava flows over immense spans of time. According to current models of Mars's geology, the planet does not have tectonic plates. This absence means that a single point for magma to escape can stay fixed for an exceptionally long period, potentially for hundreds of millions or even billions of years. This stability allows erupting lava to flow across incredible distances, blanketing huge expanses with a crust of rock. The average diameter of Olympus Mons spans approximately 600 kilometers, and its total area surpasses 300,000 square kilometers. A territory comparable in size to a mid-sized European nation like Poland or Italy. At the very heart of this geological marvel lies a gigantic depression created by 6 partially collapsed volcanic craters. This central caldera measures around 85 kilometers across and descends to a depth of 3 kilometers. Olympus Mons reaches such an extreme altitude that the atmospheric pressure at its peak is 50 times lower than at its foundation. When you consider that Mars's gaseous shell is already about 100 times thinner than Earth's, the conditions at the volcano's summit are nearly a complete vacuum. This is a primary factor complicating any mission to land a research vehicle on the red planet's highest mountain, as the atmosphere is simply too sparse for parachutes to effectively brake a descending capsule. The majority of Olympus Mons' slope is remarkably gradual, at about 5%. In stark contrast, the volcano's edges terminate in exceptionally sheer cliffs that plummet for about 7 kilometers. The exact reason for these massive escarpments remains unconfirmed. One prominent theory suggests they were carved out by the waters of an ancient Martian ocean, while an alternative hypothesis proposes they were shaped by the relentless dust storms that frequently sweep through this area. As you descend from the volcano and survey the landscape around it, you can observe a terrain filled with interconnected ridges and mountains. Some of these features stretch for as far as 1,000 kilometers from the volcano's perimeter. It is theorized that their existence may be the result of catastrophic collapses of the giant mountain's slopes or the grinding movement of ancient glaciers. If you were to travel southeast from Olympus Mons, you would arrive at the immense region known as Tharsis. This area is a volcanic plateau composed of solidified lava, covering an estimated 30% of the planet's surface, a landmass roughly the size of Africa. This plateau stands about 10 kilometers above the surrounding lowlands and is approximately 3.7 billion years old. This region is populated by numerous volcanoes, several of which are only slightly less imposing than Olympus Mons. For instance, Ascraeus Mons is recognized as the second tallest peak on Mars, featuring a central crater that reaches 110 kilometers in diameter and an overall base width exceeding 435 kilometers. For a brief period each year, a remarkable natural spectacle occurs above this volcano, as solar radiation warms its slopes, creating updrafts that whip fine dust into a thick cloud that can ascend up to 30 kilometers and be transported by winds over vast distances. Scattered across the Tharsis Plateau, you can find vertical shafts whose depths are impossible to see from the surface. The largest of these pits has a diameter of around 150 meters, and plunges at least 178 meters down. The prevailing hypothesis is that these deep shafts are actually collapsed lava tubes, remnants of ancient volcanic activity. The Tharsis region is comprised of dozens of extinct volcanoes, whose eruptions over billions of years released incredible quantities of carbon dioxide and water vapor into the Martian atmosphere. Mathematical simulations indicate that this output would have been sufficient to blanket the entire planet in an atmosphere 1.5 times denser than Earth's current one. These calculations provide strong circumstantial evidence that conditions on ancient Mars might have been far more suitable for the development of life than they are today. However, the planet's insufficient gravity ultimately prevented it from retaining this thick atmosphere, which was gradually stripped away into space. As we continue our journey, traveling eastward from the plateau, our next destination is the monumental canyon system known as Valles Marineris. You are looking at a branching network of immense canyons stretching up to 4,500 kilometers in length, 600 kilometers in width, and reaching a staggering depth of 11 kilometers. Photographs reveal that the canyon slopes in the central and western sections of Valles Marineris possess a layered composition, a distinct hallmark of sedimentary deposits formed by large bodies of water. It's highly probable that these canyons were once entirely submerged, which means the region's rocks could harbor invaluable paleontological evidence. The eastern portion of Valles Marineris meets Chaos Terra, a vast and intricate labyrinth composed of many smaller canyons. It is on these plains that you can find the remains of the Sojourner rover and the Viking 1 research probe. It was Viking 1 that, in the distant year of 1976, transmitted the first-ever color photographs of the Martian landscape back to Earth. According to the prevailing scientific hypothesis, Valles Marineris began to form during the planet's earliest stages, with geological processes and erosion later carving the canyons deeper and wider. One theory proposes that the fault system's creation is tied to volcanic eruptions on the Tharsis Plateau. An alternative explanation connects their emergence to the formation of Utopia Planitia on the opposite side of Mars. This enormous circular lowland, known as Utopia Planitia, is almost certainly the result of a colossal asteroid impact on the planet's surface. Its diameter is approximately 3,300 kilometers, and its terrain is characterized by a relatively flat and smooth relief. Utopia Planitia has been the subject of repeated study by various automated probes. Back in 1979, the Viking 2 lander sent panoramic images of its surface to Earth. Then in 2016, the Charade radar aboard the Mars Reconnaissance Orbiter, or MRO, found extensive deposits of water ice mixed with dust buried beneath the soil. Following that discovery, in May of 2021, the Chinese rover Zhurong made its landing on the plains of Utopia Planitia. It has now covered a distance of over 1,000 meters across the red planet's surface and relayed hundreds of images to us. Unfortunately, it will be unable to reach the water-bearing stratum, as this layer is situated at a depth of 1 to 10 meters. To the north, Utopia Planitia adjoins the Great Northern Plain, a massive lowland that encircles the planet's northern pole and encompasses about 40% of Mars's total surface area. If we were to journey southwest from the center of Utopia Planitia, we would arrive at Isidis Planitia. On its western fringe lies a region that for nearly 8 months has drawn intense interest from people on Earth, as it is thought to be the remnants of an ancient, dried-up body of water. Since February 18, 2021, the floor of the Jezero crater has been under exploration by the Perseverance rover, which is accompanied by Ingenuity, the very first helicopter to fly on another world in history. The Jezero crater was specifically chosen for this mission because it is one of the most promising locations to discover signs of past Martian life. It is widely thought that the crater was created 4 billion years ago, when a celestial object measuring about 49 kilometers in diameter struck the surface. The crater was presumably once filled with water, most likely during the Hesperian period of Mars's geological history, which commenced roughly 3 billion years ago, 0.7 billion years ago, and lasted for about 1 billion years. According to calculations, the atmospheric pressure during that era was comparable to Earth's, with surface temperatures reaching as high as 50 degrees Celsius. We can find confirmation of this in rock samples that the Perseverance rover recently extracted from the crater floor. These samples have yet to be transported to Earth for more thorough examination, but it is already apparent that the rocks were in contact with liquid water for an extended period. Although the rover has already supplied scientists with an immense amount of valuable data, its mission is nowhere near its conclusion. Designed for 14 years of service and having already traversed a considerable distance, our journey across the Martian terrain is not over yet. Currently, Over 300,000 minor celestial bodies within this sector have been assigned names or numerical designations, though their total population could easily exceed 1 million. The story of the asteroid belt's exploration can be dated back to 1801, when, following a lengthy and persistent search, astronomers located a puzzling object in the sky. While its parameters suggested it was a planet, it was so small that even the most powerful telescopes of that period couldn't make out its disk, causing it to appear as a bright, star-like point. This celestial body was given the name Ceres. Before long, more objects of this nature were found, which created the need for a new classification. These peculiar celestial bodies were named asteroids, a term that literally means star-like. In addition to asteroids, this region of the solar system is filled with a significant quantity of cosmic dust. As these tiny particles move slowly in a spiral, they scatter the sun's rays, which produces a very faint, matte luminescence. This glow is known as the zodiacal light, and in the equatorial areas of Earth, you can even observe it with the naked eye. For a very long time, the hypothesis that the objects in the asteroid belt are the fragments of a destroyed planet was widely embraced by the public. However, this assumption is now seen as indefensible. First, the combined mass of all the objects in the main belt is incredibly small, just 3 × 10⁻21st power kilograms, or a mere 4% of the Moon's mass. Even if we presume that a large portion of the asteroids has long since left the belt, the total mass of rocky remnants is simply not enough to construct an object close to the size of a proper planet. Furthermore, calculations indicate that the gravitational pull of Jupiter actively prevents the formation of large celestial bodies within this part of the solar system. Mathematical models suggest that the most substantial objects that ever formed here never grew larger than 1,000 kilometers in diameter. The gas giants' influence destabilized their orbits, leading to destructive collisions that gave rise to potential protoplanetary groups of asteroids with similar compositions. The main asteroid belt does not possess sharply defined edges. The vast majority of objects composing it are situated between 2.6 and 3.27 astronomical units from the Sun. These boundaries are a direct result of Jupiter's tidal forces, as asteroids in these zones are subjected to powerful gravitational disturbances from the massive planet, which warps their trajectories. Consequently, the concentration of cosmic objects in these areas is significantly lower than it is beyond them. What are known as Kirkwood gaps appear not only at the belt's conceptual borders but also throughout its interior. The two most distinct of these gaps are located at distances of 2.5 and 2.82 astronomical units. The asteroid belt itself can be conceptually split into 2 main regions, an inner and an outer belt. The dividing line between them is considered to be the Kirkwood gap at a radius of 2.5 astronomical units, which aligns with the most powerful orbital resonance with Jupiter. It is within the outer portion of the main belt that you can find the largest object in this entire segment of the solar system. For a period it was classified as a planet, and later as an asteroid. But in 2006, this celestial body was granted the status of a dwarf planet. This designation became possible because, unlike the overwhelming majority of other objects in the belt, Ceres possesses a spherical shape. Its diameter is approximately 940 kilometers, and its mass is about 9.4 × 10⁻20th power kilograms, which represents around 30% of the asteroid belt's total mass. To put that into perspective, Ceres is roughly 6,000 times lighter than our own planet. At the most distant point of its orbit, this dwarf planet travels 2.9 astronomical units away from the Sun, while at its closest approach, or perihelion, the distance shrinks to about 2.5 astronomical units. During these close passes, the temperature on its surface can climb to 239 kelvins, but the planet's average temperature is substantially lower, at just 167 kelvins, or minus 106 degrees Celsius. Scientists believe this celestial body is composed of a rocky core sheathed in a cryomantle, an icy layer about 100 kilometers thick. This composition means that water ice could constitute up to half of the dwarf planet's volume, or between 20 and 30% of its total mass. Meanwhile, situated in the inner region of the belt is the largest and most massive known asteroid in the solar system, Vesta. The object's average diameter is around 525 kilometers, with a mass of approximately 2.6 times 10 to the 20th power kilograms, making it nearly 4 times less massive than Ceres. Vesta follows a fairly elongated orbit, with its farthest point from the Sun, its aphelion, at 2.57 astronomical units, and its closest point, its perihelion, at about 2.15 astronomical units. It takes this celestial body 3.6 Earth years to complete one full journey around the Sun. Remarkably, Vesta stands out as the only asteroid that you can observe from Earth with the naked eye. This is possible not just because of its considerable size, but also thanks to its relatively bright surface, which reflects about 42% of the light that strikes it. Additionally, the minimum distance between Vesta and Earth is relatively small, at just 177 million kilometers, or 1.1 astronomical units. The prevailing theory is that Vesta has an internal structure resembling that of a fully formed planet, likely featuring a metallic core of nickel and iron, along with a rocky mantle. Currently, the surface temperature of the asteroid fluctuates between minus 190 and minus 20 degrees Celsius, though it was considerably warmer in its distant past. The dark regions on its surface, particularly in the Western Hemisphere, are very likely basaltic plains. Such features could have been created by volcanic activity, or resulted from impacts with massive cosmic bodies. The most striking feature of the asteroid's topography is the colossal impact crater named Rhea Silvia, which spans 505 kilometers in diameter and reaches a depth of about 25 kilometers. At its center rises the second tallest mountain in the solar system, standing over 22 kilometers high. You can easily see that the crater's diameter is comparable to the size of the celestial body itself, which suggests that in its past, the asteroid collided with an object of truly immense proportions. This cataclysmic event produced a vast number of small fragments that are now categorized as the numerous Vesta family of asteroids. This family includes more than 15,000 objects, which is about 5% of all known celestial bodies in the main belt. The prevailing hypothesis is that most asteroid families were born from destructive impacts between two large bodies. In some cases, gravity causes the resulting fragments to coalesce, forming a new astronomical object. However, this new body lacks a monolithic structure. Astronomers sometimes informally refer to such formations as rubble piles. For instance, Sylvia, one of the largest objects in the asteroid belt, likely fits this description, with dimensions of roughly 384 by 262 by 232 kilometers and a mass of 1.5 times 10 to the 19th power kilograms. This means that the asteroid's average density is only 20% higher than that of water. Calculations suggest that voids or empty spaces could account for anywhere from 25 to 60% of its total volume. Sylvia takes 6.5 years to complete a single orbit around the Sun. At its most distant point from the system's center, the object's orbit extends to 3.7 astronomical units, while at its closest approach, or perihelion, this distance shrinks to 3.2 astronomical units. A prevailing theory suggests that some debris from a past collision was not reabsorbed, but instead became captured as moons of the newly formed body. Sylvia is accompanied by two such celestial partners. Romulus, which measures 18 kilometers across, and the smaller Remus, with a diameter of about 7 kilometers. The internal composition of these moons remains largely unexamined, leading to the possibility that they are not solid objects, but rather collections of fragmented asteroid material, often called rubble piles. Another significant asteroid is Pallas, which was found in 1802, just after the discovery of Ceres, making it the second asteroid ever identified. This celestial body has an average diameter of about 512 kilometers and a mass of approximately 2.1 times 10 to the 20th power kilograms, which is about 25% less than the mass of Vesta. The orbit of Pallas is exceptionally stretched out and tilted at an angle of 35 degrees relative to the ecliptic plane, a characteristic that makes it a particularly challenging target for scientific spacecraft. Over its 4.6-year journey, its distance from the system's core fluctuates by more than 1.5 times, from 2.1 astronomical units at its closest to 3.4 at its farthest. The surface of Pallas is marked by a significantly greater number of impact craters compared to the larger asteroids Ceres or Vesta. Analysis of its surface composition reveals that it is primarily made of silicate rocks that contain low amounts of iron and water. It is widely believed that Pallas, much like Vesta, stands as one of the few remaining examples of a potential protoplanet, holding valuable clues about the formation processes of our solar system. Unlike Vesta, a vast majority of asteroids are impossible for you to see with the naked eye, and most remain invisible even when using amateur telescopes. Hygeia serves as a perfect illustration of this, being one of the most enigmatic objects within the main asteroid belt. It is an irregularly shaped body with dimensions of 362 by 348 by 310 kilometers, and its mass accounts for roughly 1.2% of the entire belt's mass. Despite its considerable size, Hygeia is still poorly understood, mainly because its surface is incredibly dark, absorbing around 93% of all sunlight that strikes it. Hygeia is categorized under the very uncommon spectral class F, which is a subdivision of carbonaceous asteroids. Observations of its brightness indicate that its surface has a remarkably consistent color, suggesting it has avoided any major collisions for a very long time. With a density only double that of water, it is thought to have a solid rocky core enveloped by a substantial mantle of ice, with the entire object blanketed in a thick layer of fine dark dust. It takes Hygeia approximately 5 years and 4 months to complete one full revolution around the Sun, with its farthest point, or aphelion, situated on the opposite side from the 4 largest bodies in the main belt. Its distance from the Sun varies between 2 astronomical units at perihelion and 3.5 astronomical units at aphelion. While its orbit theoretically intersects the paths of major objects like Ceres and Pallas, calculations indicate that the chance of a collision is exceptionally small. The main belt itself is home to millions of objects, ranging from dwarf planets to small cobblestone-sized meteoroids. but the average distance between them is millions of kilometers, making an accidental encounter with a traversing spacecraft extremely unlikely. Nonetheless, mathematical models predict that significant collisions do happen in this part of the solar system about once every 10 million years, acting as a constant source of new fragments. Although a crewed mission to the main asteroid belt remains a distant goal, robotic interplanetary probes have already begun to study some of its inhabitants. For instance, the Dawn spacecraft conducted detailed explorations of Ceres and Vesta between 2011 and 2016. More recently, the Lucy research probe began its journey from Earth. While its primary mission is to study Jupiter's Trojan asteroids, the spacecraft is scheduled to fly by a main belt object named Donald Johanson in 2025 to capture images of it. Furthermore, the Psyche project is slated for launch, targeting the largest known metallic asteroid in the main belt. According to the mission's schedule, the probe is expected to arrive at its destination in early 2026, where it will spend a minimum of 21 months conducting an in-depth study of the object. Even with their diminutive size, asteroids hold immense scientific and practical significance. Certain objects within the main belt are essentially pristine relics from the earliest stages of the solar system's history, and studying them will undoubtedly deepen our understanding of how planets and other celestial bodies form. Looking ahead, asteroids could serve as a vital source of materials for future space exploration endeavors. While it's uncertain how soon that future will arrive, every rocket launch brings that new era of space utilization a bit closer. For biological life to emerge and flourish, a specific convergence of factors is necessary, chiefly the availability of liquid water, a reliable energy source, and a certain variety of chemical compounds. Within our solar system, Earth is not the only place that might have provided a cradle for life. Mars is without question the leading candidate, and has been the focus of intense exploration in recent years. But there are also prospects for discovering extraterrestrial life even farther from the Sun. If you turn your attention to the next planet out, Jupiter, you will find it is a gas giant 318 times more massive than Earth, composed primarily of hydrogen and helium. Its atmosphere also contains detectable amounts of methane, ammonia, compounds of sulfur and nitrogen, and water ice, which paint a picture of a world vastly different from our own. Despite the sheer variety of chemical compounds, the probability of discovering life on Jupiter itself is vanishingly small. The prospect of biological survival is eliminated by the planet's lack of a solid surface, the intense heat of its inner layers, and the crushing pressure in the depths of the gas giant. Jupiter does, however, possess a vast network of moons. Galileo Galilei discovered the four most renowned of these, Io, Callisto, Ganymede, and Europa, back in 1609. And they rank among the largest satellites in our solar system, with sizes comparable to the Moon or even Mercury. It is also theorized that Jupiter, due to gravitational compression during its formation, amassed a tremendous amount of thermal energy, and now emits more heat than it absorbs from the Sun. This allows us to view the gas giant and its orbiting bodies as a miniature solar system in its own right. At a casual glance, Jupiter's moons might appear entirely unsuitable as places to search for extraterrestrial life, given their immense distance from the Sun, their ice-covered surfaces, and their lack of any substantial atmosphere. A more detailed investigation of these celestial bodies, however, brings astonishing facts to light. There is a strong likelihood that Callisto, Europa, and Ganymede all harbor internal oceans of liquid water beneath their frozen shells. Scientific models indicate that these subterranean seas could sustain life-supporting conditions, despite being situated much farther from their star than planets like Earth. The thick ice crust on their exteriors not only shields them from radiation and meteoroid impacts, but also provides exceptional thermal insulation, potentially creating a habitat within the massive water layer suitable for life to emerge and evolve. These possibilities position Jupiter's moons among the most compelling targets for exploration within the solar system. Let's start by looking at Ganymede, the largest and most massive body in Jupiter's orbit. Of all the moons in our solar system, it is not only the biggest, but also the one that most closely resembles a fully fledged planet. With a radius of 2,634 kilometers, it is 8% larger than Mercury, and its mass of 1.48 times 10 to the 23rd kilograms makes it twice as heavy as our moon. Ganymede features a liquid metallic core and its own magnetosphere, a distinction unique among all moons in our system. The process of nuclear decay deep within Ganymede's interior generates an additional source of heat. While the average surface temperature is a frigid 110 kelvins, or minus 163 degrees Celsius, calculations suggest its core could be heated to a considerable temperature. Data from the Galileo spacecraft's measurements of Ganymede's magnetic field points to the existence of a multi-layered, salty ocean located about 200 kilometers beneath the moon's icy crust. This ocean might consist of several distinct tiers, each with different levels of salinity, density, and temperature, separated from one another by layers of solid ice. Spectrographic analysis of Ganymede's surface has also revealed an exceedingly thin oxygen atmosphere, though this is not considered a biological signature. It's far more probable that molecular oxygen is created when ultraviolet radiation breaks down water ice, causing the lighter hydrogen to escape into space, while the heavier oxygen lingers near the surface. Beyond the vast quantities of water ice, Ganymede's surface composition includes carbon dioxide, sulfur dioxide, salts of sulfuric acid, and a variety of organic substances. It is conceivable that these compounds originated deep within the subsurface ocean, but the processes that would transport them to the moon's exterior remain a complete mystery. Another celestial body with potential for life is Callisto, the second largest moon, and the one orbiting farthest from Jupiter, with a diameter of 4,820 kilometers, nearly matching that of Mercury. Beneath Callisto's ice crust, estimated to be between 80 and 150 kilometers thick, a saline ocean very likely exists, containing significant amounts of ammonia and other dissolved compounds. Various models place its depth anywhere from 50 to 300 kilometers, with a temperature hovering around 251 kelvins, or minus 2 degrees Celsius. The presence of impurities and immense pressure would allow the water to stay in a liquid state under these conditions. Below this subterranean ocean, there is probably a layer of ice approximately 300 kilometers thick, which in turn rests upon a core of frozen water mixed with rocky materials. Callisto's surface is heavily pockmarked with craters, and is composed of ice and silicate-based rocks, along with ammonia, carbon dioxide, sulfur compounds, iron, magnesium, and trace amounts of tholins, complex organic polymers that contain nitrogen and form on celestial surfaces exposed to ultraviolet radiation. Regrettably, Callisto's great distance from Jupiter prevents it from receiving more significant tidal heating, as the giant planet's gravitational pull is insufficient to deform the moon substantially. Furthermore, since the majority of the moon is made of ice, opportunities for life to emerge are limited, because contact with solid rock, which enriches water with essential elements, is highly desirable. This low chemical diversity and cold temperature greatly diminish the odds of life arising on Callisto, though the possibility cannot be dismissed entirely. You might be surprised to learn that the most compelling target in our search for alien life is Europa. It's the smallest of Jupiter's 4 Galilean moons, just marginally smaller than our own moon. Imagine its surface temperatures. At the equator, it reaches a frigid 110 kelvins, which is minus 163 degrees Celsius, while at the poles it plunges to as low as 50 kelvins, or minus 223 degrees Celsius. You should know that Europa is tidally locked, meaning it constantly presents the same face to Jupiter. Yet observations reveal that its rotation isn't perfectly in sync, with minor deviations from its predicted path, suggesting that a liquid layer separates the surface from the core. This idea gained support back in the late 20th century from data gathered by the Galileo probe, which studied the moon's interaction with Jupiter's magnetic field. Furthermore, an analysis of the vast cracks on Europa's surface indicates that its crust once shifted a staggering 80 degrees relative to its interior, a feat that would simply be impossible without a liquid ocean acting as a lubricant beneath it. Jupiter's immense gravitational pull has a profound effect on Europa, generating massive tidal waves within its concealed ocean and creating heat through internal friction. Because of this constant kneading, calculations suggest that the internal temperature is high enough to sustain a liquid water ocean. You have to appreciate the scale of this. This subterranean ocean could be up to 100 kilometers deep and contain twice the volume of all of Earth's oceans combined. When you look at Europa, you see a world encased in a remarkably flat and pure layer of smooth ice, where the largest surface features are no more than a few hundred meters high. This icy shell is estimated to be anywhere from 10 to 30 kilometers thick. However, this crust is crisscrossed by a vast network of long, deep fractures. It's theorized that some of these fissures may penetrate all the way down to the subsurface ocean, making the ice at the bottom of these cracks an invaluable source of material for studying Europa's hidden interior. You'll also find another of the moon's remarkable characteristics to be its immense ice geysers. These plumes are only active when Europa is at its farthest point from Jupiter in its orbit, and they can blast eruptions up to 200 kilometers into space. The material in these colossal jets is astonishingly pure water vapor. Scientists are still debating whether these geysers are directly linked to the deep internal ocean, or if they originate from massive reservoirs of water trapped within the icy crust. For now, you should understand that our best estimates of the hidden ocean's composition come from studying the ice inside Europa's biggest craters. It takes a truly massive impact to punch through the thick, hard ice shell. When that happens, water from the ocean wells up, freezes, and creates a new crater floor. Spectral analysis of these areas reveals magnesium compounds, sulfur, iron, hydrogen peroxide, and potent acids, all of which point to a rich and diverse mineral content within the moon's concealed hydrosphere. Interestingly, Europa does possess an atmosphere containing oxygen, which is created when ultraviolet light breaks down the water ice on its surface. You should realize, however, that this gaseous envelope is incredibly tenuous, about 1 trillion times less dense than our own planet's atmosphere. Despite this, Some calculations suggest that the amount of oxygen dissolved in Europa's subsurface ocean could be substantial enough to sustain single-celled organisms that breathe oxygen. If life exists, you can picture underwater volcanoes as the source of its energy and nutrients, enriching the water with sulfur and iron oxides. Primitive organisms might cling to the underside of the ice shell or drift freely throughout the ocean. There's even been some daring speculation about the existence of simple multicellular life, though that remains a very bold hypothesis. Regardless, you have many examples here on Earth of species that could thrive in Europa's presumed conditions, from extremophile bacteria to complex multicellular animals like tardigrades. Consequently, one cannot dismiss the possibility that primitive life arose independently in the depths of this distant world. You should know that despite tremendous scientific interest, our exploration of Jupiter and its moons has been limited to flyby missions. No mission has ever attempted to land on the surface of any of the gas giant's satellites. At present, the Juno Automatic Station is studying the largest planet in our solar system. However, starting as soon as this July, its focus will shift to begin exploring the Galilean moons as well. Looking ahead, you can anticipate several key missions. Back in 2012, the European Space Agency initiated work on the Jupiter Icy Moons Explorer project, also known as JUICE. The mission's objective is a comprehensive study of the gas giant itself, along with its moons Ganymede, Europa, and Callisto. While JUICE is set for launch next year, it won't arrive in Jupiter's neighborhood until 2029. Assuming a successful mission, it will operate until 2033, promising to greatly expand what you know about Jupiter and its satellites. You also have another significant project to look forward to: Europa Clipper, which is being led by the National Aeronautics and Space Administration, or NASA. This robotic probe is slated to depart Earth no later than 2023 and enter the Jovian system in 2032. With Europa as its primary target, the Clipper mission is anticipated to deliver far more specific and detailed data about this moon than you will get from JUICE. Now, consider a different scenario from our solar system's history. Roughly 100 million years ago, a large, icy moon ventured too close to Saturn. The planet's immense tidal forces tore it apart into trillions of fragments. As you can imagine, the unyielding laws of physics then caused these pieces to spread out around the planet, creating an original, primordial ring. This initial ring system was about 1,000 times more massive than the one you see today, and millions of years have now passed since that cosmic cataclysm. During this period, Saturn absorbed some fragments of the shattered moon, while others peppered the surfaces of its many satellites, or were ejected from the gas giant's vicinity entirely. This represents one of the most well-supported scientific hypotheses that details the origin and evolution of Saturn's rings. Even after centuries of study, this immense cosmic formation still conceals numerous mysteries. Saturn's rings lack sharply defined edges. The visible portion spans approximately 280,000 kilometers in width. Beyond this area, however, you find exceedingly thin accumulations of dust and rarefied gas. The diameter of these features, by some calculations, extends up to 16 million kilometers, though their extremely low density makes them impossible to observe from Earth. Despite their colossal size, the combined mass of the entire ring system is quite small by cosmic measures, estimated at 3 times 10 to the power of -1/19 kilograms, which is roughly 2,000 times less than the mass of our moon. Solid objects constitute only about 3% of the structure's total volume, with the remainder being a mix of rarefied gas and cosmic dust. The disk that encircles Saturn is conventionally broken down into several major rings. Yet if you look through a sufficiently powerful optical telescope, you can easily discern that each of these is composed of a vast number of slender circles divided by narrow gaps. These separations are created by the gravitational pull of both the planet itself and its numerous moons, with some of these gaps stretching for hundreds of kilometers. Even though Saturn's disk reflects sunlight several times more effectively than the gas giant, certain rings are nearly undetectable. For instance, the ring nearest to the planet, made of the finest ice particles and methane frost, has its upper boundary notionally placed at 16 meters from the planet's hypothetical surface. Its intersection has no distinct border, merging seamlessly into Saturn's atmosphere. Just beyond this is a considerably brighter and more substantial ring, about 100 kilometers wide, which is comprised of cosmic bodies up to 2 meters across. Together, these objects account for only 0.33% of the disk's total mass. The most brilliant and prominent section of the disk, designated as Ring B, is situated farther out, beginning approximately 34,000 kilometers from the gas giant's surface, with this region extending for 25,000 kilometers. The thickness of most of this ring measures no more than 5 to 10 meters, but its outer edge remarkably forms a vertical wall reaching up to 2 meters, 150 kilometers in height. The most distant of Saturn's visible rings starts at a distance of 64,000 kilometers from the planet's surface. Its width is around 14,600 kilometers, and it exclusively contains relatively large ice fragments over 10 meters in diameter, along with several moons like Pan and Daphnis. The presence of such large objects could serve as evidence for the theory that the rings were formed from a destroyed icy moon. Alternatively, these bodies might have emerged later through the collision and fusion of smaller fragments. Past this visible ring lie the practically invisible F, G, and E rings, which are composed of cosmic dust and rarefied gas. Naturally, the majority of Saturn's large moons are in active interaction with the rings. If we venture out to a distance of 179,000 kilometers into the region of the E ring, we can discover a celestial body named Enceladus. With a diameter of only 500 kilometers, it isn't one of the gas giant's largest moons, but it commands significant interest for other reasons. Enceladus stands out as one of the few celestial bodies in our solar system that demonstrates unambiguous cryovolcanic activity. Analysis of its observed eruptions indicates that a liquid water ocean is hidden beneath its icy shell. Mathematical models suggest its temperature varies from -45 degrees Celsius in the upper layers to 0 degrees Celsius near the bottom, where it is insulated by an ice crust 2 kilometers thick at -180 degrees Celsius. Thanks to a high concentration of dissolved salts and ammonia, the ocean remains liquid even at these sub-zero temperatures. The moon's atmosphere is incredibly thin and is composed of 91% water vapor, along with nitrogen, carbon dioxide, and methane. Its gaseous envelope is constantly being replenished by powerful geysers that periodically burst from fissures in the moon's icy crust. However, the gravity of Enceladus is insufficient to hold on to this atmosphere, causing it to constantly shed particles that in turn supply material to the E-ring. Simultaneously, Enceladus continuously gathers matter from the space around it, maintaining a strange sort of equilibrium. It's understood that this geyser activity is linked to its orbital path, as tidal forces from Saturn likely deform the Moon's ice crust and trigger the eruptions. When Enceladus travels farther from the gas giant, the cracks are sealed with a new layer of ice. Crucially, it has also been established that these cryogeyser eruptions contain complex organic molecules. This discovery means the conditions within the subsurface ocean could theoretically be conducive to the development of biological life. Much farther out, at a distance of about 300,000 kilometers, you'll find Tethys, Saturn's fifth largest and most massive moon. What makes Tethys remarkable is that it shares its orbit with two other celestial objects, Telesto and Calypso. These smaller moons are situated in stable locations known as Lagrangian points, with Telesto leading the main moon by 60 degrees in its orbit, and Calypso trailing by the same angle. In contrast to the immense and spherical Tethys, these celestial objects are minor and lopsided, with diameters between 20 and 30 kilometers, and a collective mass of just a few trillion tons. Simulations indicate that Calypso and Telesto could not have initially formed in the same orbit as their far larger neighbor, suggesting they must have settled into their current positions much more recently. Tethys is an object measuring approximately 1,060 kilometers across, primarily composed of water ice with a small fraction of rocky material. The most prominent landmark on its surface is the colossal impact crater Odysseus, which spans about 450 kilometers, nearly half the diameter of Tethys itself, and descends to a depth of 3 kilometers. Another striking feature visible on the Moon's surface is an enormous fissure known as Ithaca Chasma. This canyon stretches for roughly 2,000 kilometers, about one-third of the Moon's total circumference, and extends up to 100 kilometers in width. Its depth ranges from 3 to 5 kilometers, and its floor is marked by numerous craters and minor irregularities, with two leading theories explaining its existence. One hypothesis suggests that as Tethys's internal ocean froze, the expanding ice fractured the outer crust, while another proposes that shock waves from the Odysseus impact resonated around the Moon, causing the crust to rupture. Positioned even further from Saturn is its largest moon, Titan, which presents a variety of extraordinary characteristics. With a diameter of 5,152 kilometers, it ranks as the second largest moon in the solar system, exceeded only by Ganymede. Titan is notably 5.5% larger than the planet Mercury, and stands alone as the only moon in our solar system that possesses both a dense atmosphere and bodies of surface liquid. Given its vast distance from the Sun, Titan's surface temperature is a frigid 94 kelvins, or minus 180 degrees Celsius. Despite its relatively low mass, the Moon sustains an atmosphere that is 1.5 times denser than Earth's, composed of over 98% nitrogen, along with methane and other gases. In the upper atmosphere, solar wind transforms nitrogen and hydrocarbons into complex organic compounds that drift down to the surface, creating an opaque haze that prevents observation in the visible light spectrum. The prevailing model of Titan's interior points to a substantial rocky core, roughly 3,400 kilometers in diameter, at its center. This core is enveloped by a vast layer of highly malleable water ice blended with methane hydrate. At such extreme low temperatures, this ice acts as a solid geological material, forming mountain ranges, while liquid ethane and other hydrocarbons pool in low-lying areas and crevices. The combined forces of the solar wind and Saturn's powerful magnetic field continuously strip away Titan's atmosphere, Yet this loss is steadily counteracted by replenishment from the moon's internal processes, a cycle that could persist for billions of years. When the sun expands into a red giant, it will likely vaporize the hydrocarbon haze and melt Titan's frozen landscapes, potentially making the moon a more hospitable environment for life, though this event is still an immense stretch of time away. Pluto, a dim and elusive object, orbits at an average distance of about 40 astronomical units from the Sun. This remote world follows a highly elongated path around the solar system's center, requiring 248 Earth years to complete a single revolution. Through extensive observation, Pluto's radius has been determined to be 1,188 kilometers, making it substantially smaller than all the solar system's planets, and even several moons, including our own. Its mass has been calculated with great accuracy and found to be remarkably small, just 1/5 that of the Moon. Because its properties align more closely with smaller bodies like Eris, Ceres, or Sedna, Pluto was reclassified in 2006 to lead the new category of dwarf planets. Pluto's extended and eccentric trajectory defines its lengthy orbital period. The planetoid reached perihelion, its closest point to the Sun, in 1989 for the first time since its discovery, at a distance of 29.7 astronomical units. Its distance from the Sun has been increasing ever since, and will peak in the year 2113 when it nears aphelion, located 49.3 astronomical units from our system's center. Consequently, Pluto remains a profoundly remote and faint celestial body. It is invisible to the naked eye from Earth, and even images from the Hubble Space Telescope depict it merely as a fuzzy, brown-colored disk lacking any clear surface features. These challenging conditions make comprehensive study from a distance practically impossible. To overcome these limitations, the New Horizons automated space probe was dispatched toward Pluto in 2006. After a 9-year journey, during which it also captured detailed images of Jupiter, the spacecraft finally reached its primary destination in 2015. While flying past the dwarf planet, the probe executed around 400 distinct observations, and the subsequent transmission of this massive dataset back to Earth required more than a full year to complete. The probe's specific trajectory meant we couldn't photograph the entire surface of the dwarf planet. You see, the New Horizons spacecraft didn't enter orbit around Pluto. Instead, it flew past to have the chance to investigate other objects, which leaves us needing to understand its internal composition. The prevailing model suggests Pluto has a massive core at its center, with a diameter of about 1,700 kilometers, made of various water ice forms and rocky materials. This core is enveloped by an icy mantle 300 kilometers thick, where poorly understood tectonic activities might be occurring. This mantle is then covered by a crust of crystallized nitrogen, methane, and carbon monoxide ices, where surface temperatures plunge to 60 kelvins, or minus 213 degrees Celsius. Our exploration of Pluto will commence with its most prominent and well-documented feature, the Tomball Regio. This immense territory is situated in the planetoid's equatorial zone and has a shape that brings to mind a stylized heart, a resemblance that earned it the nickname, the Heart of Pluto. Spanning 2,300 kilometers, this plain covers roughly a quarter of the celestial body's entire surface area, making it an unmissable landmark. Upon closer inspection, the surface of Tomball Regio is far from uniform. Its western section is dominated by the smoother and brighter Sputnik Planitia, a feature with a diameter of 1,492 kilometers. If you consult an elevation map, it becomes clear that this area is a vast lowland. It is blanketed by a dense layer of nitrogen ice, along with carbon monoxide and solid methane. These materials are naturally light in color, allowing some parts of the plain to reflect as much as 90% of the sunlight that strikes them. The near-total absence of craters here also tells us this region is geologically very young. The leading hypothesis for Sputnik Planitia's origin suggests it formed about 100 million years ago, following Pluto's collision with a large celestial object. This impact would have carved out a colossal crater, which was then filled by the flash-frozen contents of the dwarf planet's theorized internal ocean. You can see evidence for this in distinctive surface patterns, such as polygonal cells measuring 20 to 30 kilometers across, with hills and depressions concentrated between them. This structure is reminiscent of convection cells that form in any liquid heated from below, offering indirect support for the idea of a warm Plutonian interior. Tombaugh Regio is flanked by relatively tall mountain ranges. The Al-Idrisi Mountains ascend to heights of 3 kilometers, while in the southern part of the heart, the Tenzing Montes stretch toward the sky. Certain peaks in this latter range soar more than 6 kilometers above Pluto's average surface level, establishing it as the highest mountain ridge on the dwarf planet. What's remarkable is that these mountains are likely composed primarily of water ice, which at such extreme low temperatures possesses a strength comparable to solid rock. Moving a bit farther south, you can observe a deep basin encircled by massive, multi-layered ridges of ice and stone. It is speculated that this might be the caldera of an ancient cryovolcano, with the surrounding terrain littered by numerous frozen eruptions. The chemical makeup of these deposits is of immense scientific interest, as analyzing it could help us unravel the complex details of Pluto's internal structure. The eastern portion of Tombaugh Regio presents a noticeably darker hue. Furthermore, its surface is pocked with many craters, indicating that this region is considerably older than Sputnik Planitia. If you were to continue eastward along the equator, you would encounter a chain of dark spots, each hundreds of kilometers in diameter. These features are known as maculae, and are named after shadow deities from different cultures. One, for instance, is called Balder, and together they create a colossal structure that encircles the planetoid along its equator, known as Cthulhu Macula. Stretching west of Tombaugh Regio is Cthulhu Macula itself, the largest dark marking on Pluto, with a length of nearly 3,000 kilometers. Its surface reflects no more than 30% of the light it receives, creating a sharp visual contrast with the bright, adjacent Sputnik Planitia. While there is no definitive information on what the maculae are, their high concentration of impact craters confirms their ancient origins. We do know that the surface of Cthulhu Macula is varied, featuring a hilly landscape in its western part, a smooth plain in the middle, and a mountainous, cratered region to the east. Leaving the somber Cthulhu Macula behind, we can journey north to find the Lowell Regio, a sprawling valley that surrounds Pluto's North Pole. Curiously, this location is currently the most brightly lit area on the entire celestial body. This is because Pluto's axis of rotation is tilted at a very steep angle relative to its orbital plane. As a result of this tilt, the dwarf planet has turned its north pole directly toward the Sun for this portion of its long year. This prolonged solar exposure is thought to have a significant effect on Pluto's atmosphere. The current theory is that the Sun's rays are causing the nitrogen ice settled at the pole to sublimate, replenishing the dwarf planet's gaseous envelope. This process likely explains why Pluto's atmospheric density has tripled over the last 30 years, even as it has been moving farther away from the Sun in its orbit. When you compare it to the planets of our solar system, Pluto exhibits a number of unique orbital characteristics. Not only is its orbit noticeably inclined to the plane of the ecliptic, but the planetoid itself is in a state of constant cyclic oscillation around a particular point. This wobble is directly related to the gravitational influence of its very large moon, Charon. This moon is named Charon, and it possesses a mass of 1.52 times 10 to the 21st power kilograms, which accounts for over 11% of Pluto's total mass. These two celestial bodies orbit a shared center of mass that is situated in the space between them. They are tidally locked with one another, meaning they perpetually face each other with the same hemisphere fixed in view. In contrast to Pluto, Charon's surface is significantly darker and predominantly covered in water ice, with mixtures of methane and nitrogen appearing only in specific areas. Beyond Charon, the system includes several other moons, though they are all considerably smaller and have irregular shapes. Nix and Hydra, found in 2005, measure several tens of kilometers across, while the more recently discovered Kerberos and Styx are no larger than 16 kilometers in diameter. It is believed that all these bodies are composed mainly of water ice and were captured by Pluto's gravity from the Kuiper Belt. Regrettably, the far side of Charon remained hidden from the cameras of the New Horizons probe. Nevertheless, the visible hemisphere reveals a multitude of fascinating geological formations. For instance, south of its equator lies a vast territory known as Vulcan Planum. While its precise area is unknown, it covers at least 400,000 square kilometers, a size comparable to a medium-sized European nation. Within this region, you can find Charon's highest peak, Kubrick Mons, which has a diameter of roughly 40 kilometers and an estimated height of roughly 40 kilometers, reaching 4,000 meters. The mountain is notably encircled by a broad, ring-like trench that plunges to a depth of up to 2 kilometers. One prominent hypothesis suggests that Kubrick Mons could be a cryovolcano, which would imply that the surrounding terrain likely subsided due to the collapse of a subsurface reservoir. Further to the north is the sprawling expanse of Oz Terra, a landscape heavily scarred by countless impact craters. This territory is separated from Vulcan Planum by a series of immense cliffs and chasms, which create a vertical drop of about 1 kilometer. The most substantial of these features is Serenity Chasma, stretching for 200 kilometers in length and varying from 40 to 50 kilometers in width. Its depth can extend down to 7 kilometers, although its floor is difficult to study because of the deep shadows cast by its steep walls. Even farther north, near the pole, you will find the colossal feature known as Mordor Macula, which measures 475 kilometers across. Its origin remains a topic of considerable scientific debate. The leading theory proposes that nitrogen and methane escaped Pluto's atmosphere, were altered into complex organic molecules called tholins by solar radiation, and then slowly accumulated on Charon's icy surface. This idea awaits confirmation, which will be a key objective for any future missions to the system. Charon continues to be an object of great mystery, even as the Pluto-Charon system stands as one of the most compelling structures in our solar system. Unfortunately, it remains inadequately explored. The New Horizons spacecraft has long since departed its vicinity, and these celestial bodies are now receding from us, taking their secrets with them. At present, the probe is 52 astronomical units away from Earth, from where it continues to transmit infrequent yet critically important data. Around the year 2030, The probe's systems are expected to shut down for good, leaving the spacecraft to drift in complete solitude through the cold, empty expanse of interstellar space. In 2018, the New Horizons Robotic Research Station became the fifth human-made object to pass the 50 astronomical unit mark from the Sun. This symbolic threshold was previously crossed by the Voyager probes and, before them, by the Pioneer 10 and Pioneer 11 research craft. It is highly probable that none of these other deep space pioneers are still functioning, having long since fallen silent. The New Horizons mission commenced on January 19, 2006. Today, the spacecraft is 52 astronomical units from our planet, traveling outward at a velocity of 14 kilometers per second, or about 3 astronomical units each year. Its primary targets were Pluto and its moon Charon, and although that main mission was successfully completed, the spacecraft itself remains operational. As is common for most interplanetary research stations, New Horizons executed a gravitational maneuver around Jupiter before proceeding to its ultimate destination. This flyby enabled it to dramatically boost its velocity while capturing high-resolution images of the solar system's largest planet and its moons. In fact, the probe's cameras were used to capture the very first video footage of an active volcano erupting on Jupiter's moon, Io. Only after gaining this additional momentum did the craft set its course for Pluto. The station finally arrived in the vicinity of the dwarf planet in January of 2015. The mission's chief objective was a thorough investigation of both Pluto and Charon, which involved detailed photography and surface mapping of these distant worlds. The probe was also tasked with measuring magnetic field parameters and solar wind interactions near the bodies, along with gathering data on their atmospheres and surface reflectivity. Of course, the research plan also involved searching for any undiscovered moons and refining Pluto's orbital data. Upon completing its primary assignment, the mission was extended to continue research beyond Pluto's orbit, focusing on objects within the Kuiper Belt. This phase yielded images of celestial bodies like Quaoar and Arrokoth. Furthermore, the spacecraft's cameras were utilized to measure the distances to the stars Proxima Centauri and Wolf 359. Regrettably, beginning in 2026, the onboard power supply will start to degrade, forcing a gradual shutdown of its scientific instruments. Nevertheless, the New Horizons station will persist on its journey beyond our solar system, and by 2038, it will have reached a distance of 100 astronomical units from the Sun. Sometime around 2025, the power supply aboard the New Horizons station will likely fail completely, making any communication with it impossible. This probe will never revisit our solar system, a destiny shared by 2 earlier interplanetary explorers, Pioneer 10 and Pioneer 11, which are also on a one-way trip out into the cosmos. These 2 probes were the very first automated research stations that humanity dispatched into the vastness of interstellar space. The Pioneer 10 mission commenced on March 3, 1972. At present, this spacecraft is located 127 astronomical units from Earth and is receding at a velocity of roughly 12 kilometers per second, which translates to about 2.5 astronomical units each year. Jupiter was its primary destination, a mission now designated as successfully concluded, although the craft itself is no longer operational. After a journey of 641 days, the probe arrived in the Jupiter system on December 4, 1973. Throughout its mission, it captured photographs of the gas giant's surface and its largest moons, while measuring the atmospheric composition and the planet's magnetic field. It also revealed that Jupiter radiates 2.5 times more heat into space than it absorbs from the Sun, a set of unique data that became foundational to our understanding of gas giants and their satellites. The trajectory for the second probe, Pioneer 11, also included a flyby of Jupiter, but its main objective was Saturn, our system's other prominent gas giant. The probe's instruments collected data on the planet's magnetic field, and its cameras provided a wealth of images covering not just the planet and its rings, but also its moons, Titan and Mimas. Current calculations place this probe at a distance of about 106 astronomical units from the center of our solar system. Once their main objectives were met, both Pioneer probes continued their voyages, venturing ever farther from the Sun. Regrettably, the final transmission from Pioneer 10 was picked up in 2003, and communication with the second probe had already ceased back in 1995. It is now presumed that while these probes are rapidly exiting the solar system, they lack the velocity to ever overtake two other spacecraft that were launched much later. The Voyager 1 mission launched on September 5, 1977, with Jupiter and Saturn as its primary targets. This spacecraft is currently 154 astronomical units from Earth, traveling away at a speed of approximately 17 kilometers per second, or 3.6 astronomical units annually. The mission is considered a success, though the spacecraft now operates in a limited capacity. It's difficult to overstate Voyager 1's contribution to our exploration of the solar system. It was responsible for discovering several of Jupiter's new moons and a previously unknown ring system. Its cameras documented volcanic eruptions on the moon Io and offered definitive proof that Jupiter's Great Red Spot is, in fact, a gigantic storm. The probe sent back hundreds of images of our solar system's largest planet and its moons to Earth. Long after Voyager 1 crossed Neptune's orbit, its instruments continued to send back a trove of valuable data about interstellar plasma. Having already left both the Kuiper Belt and the heliopause far behind, the probe is now swiftly traversing the solar system's scattered disk, on a course toward the inner edge of the hypothetical Oort cloud. It stands as both the most distant human-made object from Earth and the fastest artificial craft leaving our solar system. As the first spacecraft to exit our system, Voyager 1 has given scientists an unparalleled chance to investigate the heliopause. This is the region where the pressure from the solar wind finds equilibrium with the pressure of interstellar gas. It is a place of collision between charged particles from our star and various plasma particles and magnetic fields, the study of which is profoundly important for grasping the processes at work throughout the universe. Unfortunately, around the year 2025, the radioisotope thermoelectric generator that powers the station is expected to be fully depleted, at which point all contact will be permanently lost. Projections indicate that in 300 years, the probe will breach the inner boundary of the Oort cloud. It will then take approximately 30,000 years to pass through this region, after which it will have finally departed the confines of our solar system. Roughly 10,000 years after that, the station will fly within 1.6 light-years of the star Gliese 445, before vanishing forever into the cosmic depths. Speaking of Voyager 1, it's impossible not to mention the mission's other spacecraft, which departed from Earth in August of 1977. The designated targets for Voyager 2 were Saturn, Uranus, and Neptune, though it also swung by Jupiter to gain an additional gravitational assist. The images captured by this probe supported the hypothesis that subsurface oceans might exist on Jupiter's moons Ganymede and Europa. Upon its arrival at Saturn, Voyager 2 collected data on the gas giant's temperature and magnetic field, in addition to discovering several of the planet's previously unknown moons. Of course, it also took countless photographs of both Saturn's surface and its intricate ring system. The probe's ongoing trajectory took it past Uranus and Neptune, yielding many unique images, and leading to the discovery of 17 moons and ring systems near both ice giants. Neptune's gravitational influence ultimately redirected Voyager 2, forcing it to leave the plane of the ecliptic and thereby sacrificing any chance to visit other objects in our solar system. However, its mission was far from over. In the years that followed, Voyager 2 continued to supply crucial data on interstellar plasma and the cosmic wind, and even played a role in measuring the distances to various stars. At this moment, the probe is positioned 128 astronomical units away from the heart of our solar system, a distance that grows by 1,537 kilometers with each passing second. Its long voyage will bring it near Ross 248, a dim red dwarf in the Andromeda constellation, in roughly 42,000 years. The craft is projected to pass this star at a minimum distance of about 1.7 light-years, and after about 300,000 years of travel, it may come within 4 light-years of Sirius. It's a sobering reality that we can no longer detect such a minuscule object from Earth across such an immense gulf of space. You and I are living in the very infancy of space exploration, where these interplanetary probes represent humanity's first hesitant steps into the vastness of the cosmos. Their journey is a testament to our initial ambition to understand the universe that surrounds us. What fate awaits these pioneering craft? They could be obliterated by a collision with some unforeseen cosmic debris, or perhaps our far future descendants, having mastered interstellar flight, might retrieve them for display in museums. The more probable scenario, however, is that their delicate structures will drift for ages through the silent, empty void. Over millions of years, relentless cosmic radiation and countless impacts from dust particles will degrade them, until they are reduced to a fine powder that vanishes into the universal depths. Keep in mind that our galaxy is home to no fewer than 200 billion stars, some of which are solitary, while others boast planetary systems as rich as our own. The Milky Way contains at least 1 trillion planets, the vast majority of which remain undiscovered. This incredible fact underscores that our exploration has only just begun, and your support is the crucial element that enables this journey to press onward toward the most remote and unknown worlds. Let's find out what secrets they hold.